This video is going to be our lecture about momentum and impulse. So let's go ahead and get started. All right, so before we get into this, I wanted to start with a little demo here and a question. So I have I should have a tennis ball, but I don't have a tennis ball, so I got a golf ball since it's the best sport ever. Right here. Got my golf hoodie on, nice, and a basketball. Okay, so your goal here is this. So let me go ahead and stand up. You need one of these objects to hit the ceiling, but you can only drop it from shorter height. So obviously, dropping them, just normally won't work. So, pause the video here real quick to think about ways you could possibly do this. And I'm going to go in and show you how you can do it. All right. All right. So hopefully you're back. You had some ideas. And here's what we got. So what I'm going to do is I'm going to set the golf ball on top of the basketball here. Hold it out. Like I said, it hits the ceiling, okay? Now, when we do this, let's make some observations, all right? So, what do you notice between these two? Well, right away, you notice that they have a different size. In other words, a different mass, right? So different masses. And then if I look here, if I normally drop the basketball, it bounces up to about my waist. If I normally drop the golf ball, it only bounces up about that far. But if I look at what happens to the basketball and the golf ball afterwards, when I do this, when I change the situation a little bit, obviously the golf ball goes a lot higher, and if you couldn't really see because it was out of the frame, the basketball only goes up this much, so it changes, right? So in other words, the velocity that they leave the ground with changes. So our observation is they're going to have different masses. They have different masses, and they have different velocities depending on the situation here, okay? So what we're going to look at is we're going to look at how mass and velocity interact with each other to produce what we call momentum. All right, so this is going to be our unit on momentum and impulse. Let's go ahead and get started. So this is what we're going to do: define momentum, calculate momentum, define impulse, stuff like that. You can read it. Great, fantastic. So momentum. All right. Literally, momentum, the definition. So they use this term a lot in sports, okay? You hear it a lot, like, oh, this team has all the momentum with it right now, right? And what that means is it's really hard it seems like the team's getting all the breaks, everything good is happening for that team, right? So in other words, it's really hard to stop them. They got all the momentum, right? So that really holds true in the actual physics definition of it. And basically what momentum is how hard it is to stop an object, okay? So when we look at this, when we look at the equation here and the variables that we are observing in that little demo, right? So, and if you think about how it is to stop, factors on how to stop something, what are the two factors that would factor in to how hard it would be to stop something? Well, mass and velocity, right? So the thing that has more mass would be harder to stop. Just think about common sense here. Is it harder to stop a little car, or is it harder to stop a freight train? Well, obviously the freight train, because it has more mass. Okay, so that makes sense. That variable makes sense. What about velocity? Well, which one's easier to stop? The car going at 5 meters per second or the same car going at 50 meters per second? Kind of common sense there. It's harder to stop the car when it's going faster, right? So those two directly affect how hard it is to stop something. So when we multiply the two together, we get momentum. So our equation here, and this is not a letter P, it's the Greek symbol rho. It should actually look like this. All right, mass and velocity. What you have to remember is velocity is a vector, so it has direction. All right, so that means you're positive and negative. All right. Again, this is just a basic definition here. Your units here are kilograms times meters per second. Pretty straightforward. Mass is in kilograms, velocity is in meters per second. And this was a vector, so momentum is also a vector. All right. So remember how hard it is to stop a moving object. The more momentum you have, the harder it is. Okay. So let's just try basically getting used to the equation here. Just double checking. You list what you know. It says a car of mass 500 kilograms traveling at 2.5 meters per second. Calculate the car's momentum. I want momentum equals mass times velocity. I have my mass here, my velocity here. So quite simply, mass 500 times 2.5, and I get. You can calculate that. What do we get when we do that? List your known variables. There's your answer. All right, pretty easy, pretty straightforward, right? Mass times velocity, easy stuff. The key here is it has to be in kilograms and it has to be in meters per second, base units. All right, easy stuff. So just like we did in the energy chapter, we're going to be relating this to a law of conservation of momentum. So we had law of conservation of energy, and now we're on law of conservation of momentum. All right. So if we think about Newton's first law, what it says is if no net force acts on the body, its velocity is constant, right? So if there's nothing acting on it, no net force, it remains at a constant velocity. So if it remains at a constant velocity, what do you think happens to its momentum? Well, it also remains constant, right? So if it has no net force acting on it, in other words, not changing its velocity, its momentum is not going to change either, right? So what we can say is momentum is conserved. So if there's no outside force acting on the object or the system, we can say that momentum is conserved. And that gives us the conservation of momentum, the law of conservation of momentum, right? And it says in a closed, isolated system, just like the energy, the law of conservation of energy, there's no external force, no net external force acting on it, we can say momentum is conserved. So in other words, the equation we get that is this. We get momentum initial equals momentum final. And, from that, we can get something like this. Like we're going to be creating our own equations here, just kind of like we did in our energy chapter where we picked the point. We said, at the top of the roller coaster, what kind of energy did it have? Well, it had kinetic, it had potential, it didn't have spring, right? So we would, write that out. At the bottom, what did it have? Well, it had this, this, and this, and then we write that for a final. So it's kind of the same thing here. You're going to be comparing a before and after instead of like at any different point. So, and there's usually an action, right? So, the ball bouncing or whatever. So maybe in this case, we have something like this. Let me draw it out. So if I'm looking to get something like this, maybe I would have, two cars going at each other. And then after, they're going to collide and go separate ways. So what this is doing is you need to find the total momentum initial, right? The total momentum initial and the total momentum final and add it up. Well, I have car 1, car 2, car 1, car 2. One's positive, one's negative, one's positive, one's negative. So when you're working with this, you think to yourself, well, on the initial side, how many objects have momentum? Well, there's two things moving, so two objects. So I have to equate that. So I have to represent that. So I say mass 1, velocity 1 plus mass 2, velocity 2. So I've accounted for each object that has momentum, right? The action is the equal sign. And then afterwards, how many objects do I have momentum? I have 2, so I do M1 V1 final plus M2 V2 final. And this is just an example. It's a real rough example, just showing you like, okay, how are we going to be building equations, finding velocity, finding mass, whatever we need to do from this law of conservation of energy. It's just saying that the momentum before is equal to momentum after. And yeah, that's basically it. Don't worry, we'll be doing a bunch of problems with this and stuff like that, okay? All right, so let's read this problem here and see what we got here. So it says, two blocks of mass 3m and m head towards each other, sliding over a frictionless surface with speeds 2v and 5v respectively, and stick together. In which direction will the two masses slide across the frictionless floor after? So it tells us that there's two things moving and they stick together. So let's make an equation here and kind of look at this. So if I was to make an equation for this before and after, so I'd say momentum initial equals momentum final. So initially, there's two things moving. So I'd have 3m 2v plus m 5v. That's before, because there's two things. That one's moving, and then this one's moving. All right, equals, they stick together, so I have to do 3m plus m, and they move with the same velocity, so I just put velocity final. So does everybody understand how I made that? So this unit of momentum here describes this object. This unit of momentum here describes this object. After they collide, what happens is they stick together. We don't know which way they move, right? But if they stick together, how I mathematically represent masses sticking together is adding them, and they travel with the, since they're stuck together, they travel with the same velocity, okay? So this is just an example of how to make this equation. Now I'll talk about how we're going to figure this out. So let's look at this, right? We know the total momentum, so we know this has to happen, right? So we can figure out and say that this way is positive and this way is negative. And we can figure out which object has more momentum, right? Then we can figure out that, oh, it has more positive momentum. So afterwards, it has to have positive momentum. Therefore, it has to be moving to the right. So if I look at this, I have 6 mv when I multiply it together. I look at this, I have 5 mv. So, and this is going to be, since it's moving this way, it's going to be negative, right? So there is more positive momentum. So that means the total initial momentum is going to be positive. So that means the total final momentum has to be positive. Therefore, it has to be moving to the right. So therefore, my answer is going to be B. See if I got it right. Yep, B. All right, perfect. Next term. So we talked about momentum, and now we're going to talk about impulse. All right, this is also a vector. The units are the same, kilograms per meters per second. And basically what it is any force exerted over a certain amount of time. Okay, so if you exert a force over a certain amount of time, then you've imparted impulse on an object. Okay. The total amount of impulse is also equal to the change in momentum. So if I get my equation here, is J is impulse, and it's equal to force over some amount of time, okay? So there is going to be a change of momentum, right? We said if there's no outside force, momentum stays the same, but here there is going to be a change in momentum, right? And it's equal to the force over time. I also know that impulse is equal to the change in momentum. I'm going to show you how we derive that a little bit later, but all you got to remember is impulse is J. It is a vector, so it's positive or negative. Our equation is F delta T. And I'll go into how it becomes this in a second here, okay? So here's how it happens. So we talked about impulse is imparting a force on an object, right? So our basic equation for force is F equals ma, right? And I know acceleration is just the change in velocity over time. Basic, right? So I'm gonna substitute that in, right? So I'm gonna substitute this in for A. okay? And then I get this right here. And what I want to do here is, can I get impulse, right? If I solve this for t, I multiply by t, watch what happens. I get impulse on one side and momentum on the other, right? So this is the impulse momentum theorem. F delta t equals m delta v. Well, m delta v is change in momentum, right? Well, it should be, because if I look at this, right? M delta v. Well, delta v is v final minus v initial. Okay, that makes sense. So if I multiply in, I get mv final minus mv initial. Well, what's mass times velocity? What's mass times velocity? Oh, it's momentum. And this is final minus initial. Anything final minus initial is change in momentum. So that's why this right side is the same thing as saying change in momentum. F delta t, we remember, is J, right? It's impulse. So that's how I can say impulse is equal to the change in momentum. So this is the impulse momentum theorem. See if I bring anything else up. Yeah, F delta t is impulse. Yeah, and that's literally just what I wrote in circles and arrows. It's just in a straight line there, right? So J equals F delta t, and it also equals a change in momentum, okay? All right. So what I have here is two videos that no longer work. Let me see. They work? No, they don't work. All right, because they're real old. And I probably switched computers on them. All right, so I'm going to explain kind of what happens here. All right, I'm going to explain what happens here. And if it wasn't freezing cold, I'd probably do it. But it's freezing cold and we're on a snow day. And I'm kind of limited on time because I'm leaving in a couple days. So here's what we got. We got, as you can tell, I just got back from golfing because I got my flip-flops and my golf polo on. So it must have been a good day, except I had to do a little physics experiment. So what I have, well, so what the scenario is this. It's a real basic scenario. So I'm going to throw an egg, right, a raw egg, two different ways, right? Well, I'm going to throw it the same way. So I'm just going to throw it. It's going to have the same velocity, right? I'm going to throw it with the same velocity, okay? In both scenarios, the egg is going to stop. So let's think about this. So if I have this, oh, sorry. So if I have this, right, I have, change in momentum is equal to mvf minus vi, right? So if I'm going to throw it with the same velocity, and it's going to come to rest both times, it's the same mass because it's an egg. It's the same egg, right? Would you agree that in two different scenarios, so if I throw it and it stops, no matter what happens, it's going to have the same change in momentum, right? Because I'm going to throw it with the same initial velocity, and it's going to come to a stop. So therefore, the change in momentum is going to be the same no matter how I stop it, okay? So let's go ahead and look at this. So in the first video, okay, that no longer works, I'm going to throw an egg I throw it at this pile of wood, right? So this pile of wood, right? Little logs, I throw and I hit it. Pretty much common sense what's going to happen to an egg if you throw it at a pile of wood, right? It's going to break, okay? So let's take a look at this real quick. So what it shows, or what you have to visualize, is that the egg stops in a very short amount of time, right? A short amount of time, okay? To do that, the wood has to impart a very big force on it, right? A big force, small t, gives me an impulse. And remember, impulse is change in momentum, right? So therefore, each egg is going to have the same impulse and the same change in momentum. We're just going to mess with this over here. We're going to mess with this. So what I wanted to see is this egg broke, right? This egg broke. So now what I did in the next video that doesn't work is instead of throwing it in a pile of wood, right, in a doorway, I hung a fitted sheet, right? The fitted sheet that's impossible to fold. It has like the elastic in it, goes over your bed. All right. So I hung it in a doorway, so it's just hanging there, right? So I threw the egg with the same velocity, same impulse, same change of momentum, right, at the sheet. Well, the egg didn't break this time. Why? Well, when I hit it, the egg was in contact with the sheet for a longer amount of time, right? It hit, it gave with it, went and curled under, right? So therefore, if I increase the time, right, I increase the time, I made this variable big. To get the same impulse, the force has to decrease. So I have a smaller force acting on the egg that the egg is able to survive. So what I've done is I've increased the variable that's going to make my egg survive. I've increased the time in contact, therefore requiring less force applied by the sheet onto the egg, and therefore the egg survives. And this is the same like if you play sports, right? You know, baseball, what's great to have? You want to have soft hands, right? You want to have soft hands when you accept the ball, right? If you have stiff hands and you have your hand here, the ball is going to hit and bounce out, right? But if you move your hands with the ball as you're going to field it and throw, right? You want to accept the ball, so you're increasing. So as you're moving with it, you're increasing the time the ball is in contact with your glove, therefore decreasing the force. So therefore the ball stays in your glove and you can make the play. Same thing as like, I mean, soccer is a dumb sport, but it's the same thing, right? You don't want to have a stiff foot and have, you know, try to like, you know, just meet the ball and not give with it, right? When you receive a pass, you know, because everybody's mastered this by the age of 4 because it's the easiest sport to play, right? When you come, you cradle the ball, right? Your foot gives with it and you accept it, and then the ball stays there and you don't lose control of it. If you have a stiff foot and just meet it there, it's going to hit your foot and bounce off, right? So no go, all right? It doesn't matter because nobody scores goals in soccer anyway, even though the goal is as big as a wall. So you know, we've already discussed this, so you guys already know about that. All right. I can just see everybody watching this video typing in the chat. This time doesn't matter. It's just a video. You can't talk crap back. You have to sit there and listen to it though. All right. Oh man, it's only day 1. You guys miss me? Impulse, man. This is a question, I think. Yeah. All right. So here we go. It says a bouncy ball mass m is initially moving to the right towards a wall with the speed of 2v. The ball recoils off the wall, with a speed of v. What is the magnitude of the impulse of the ball on the wall? Do you see I got tired because I started talking about soccer and it got boring. I was like, oh man, soccer. All right, wake up. Sports, good sports. Golf. Watch golf. Tiger Woods. Sweet. All right, I'm awake. All right, so let's look at this here. So the key to this, how kids get this problem wrong, an impulse problem, is they forget that velocity is a vector. So in other words, one of these have to be positive and one of these have to be negative if they change direction, okay? So it's saying what is the magnitude of the impulse, right? So I remember impulse is equal to force delta t, but it is also equal to change in momentum. Well, you want okay, that comes first. Nice, good job. Which is equal to m v final minus v initial. So let's look at this. Let's look at this right here. I have m. It's the same m. V final is v, negative v, I'm sorry, minus 2v. See, I almost did it. I almost didn't put the negative there, all right? So if I look at this, I got 3, so I get negative 3, so I get m equals, so it's going to be equal to, see, again, that negative is just my direction. That means they probably put the positive and negative opposite, so therefore my answer here is going to be C. Let's see if I got it right. Yep. All right. Let's keep rolling here. All right, so now let's look at some graphs. So if we have a non-constant force, right? We have a non-constant force here. Okay, the force is changing as time, so this is a force versus time graph. So the area under this graph, the purple shaded area, is going to be equal to impulse. Okay, so if you get a force versus time graph, if they ask you to calculate impulse, it's equal to the area under the curve. And again, like it states on the graph, if you have something above the x-axis, it's positive. If you have something below the x-axis, it's negative. Okay? I mean, that's pretty straightforward. Okay, literally just what I said. All right. Force versus time graph, it allows us to calculate for a non-constant force. Okay? All right, let's keep going here. We got an example. It says a toy rocket of mass 2 kilograms is initially heading to the right with a speed of 10 meters per second. So I know at this point here, let me kind of just build this out. So I know at time equals 0, my velocity here is 10 meters per second. It starts with a velocity. A force in the horizontal direction is exerted on the rocket as shown in the graph below. So it has a non-constant force on it. What is the velocity of the rocket at time equals 10 seconds? We want to know velocity final here. Okay, so right away, we know that we could find impulse, right? If we have a force versus time graph, if we find the area under the curve, right, that equals impulse. So let's go ahead and do that. Let's look at the area here. Well, actually, is it the same? It's 4. This is a base 4, height 30. This is a base 4, height 30. So this area and this area, does it make sense that it cancels out? Because it's the same, and one's positive and one's negative, so it cancels it out. So all I'm left with is this last part here. And I got a rectangle of 2 by negative 30. So my area is equal to, what is that, negative 60 is my impulse. So now, well, how do we get that to relate to velocity? Well, what we do is we look at this. We know that impulse is equal to change in momentum, which is equal to VF minus VI. All right. So if I look at this, my impulse is negative 60. My mass is 2. My velocity final here, what was my velocity final? Oh, that's what I'm looking for. Goofy. Minus my initial velocity, which was 10, right? So I can go ahead and do this. So I divide by 2, I get negative 30 equals VF. VF, what? Oh, minus 10. So I add 10. So plus 10, and I get, what is that? Negative 20 meters per second. Yeah, I should get C. All right, so let's check to see if we get the right answer here. All right, so, yep, we got negative 60. Initial momentum was 20. Final momentum is that. D, how do we get D? Hold on, previous. Whoa. Oh, I think that's wrong. Oh, okay. All right, see what I did. All right, here we go. So, oops, sorry. Erase this real quick. So what they did is this. Knowing that our impulse was, our impulse was erasing. Our impulse here was negative 60. So the change in impulse, I'm sorry, the impulse is equal to change in momentum, right? So I wrote that. I just did it wrong. All right, J, oh my gosh, stop. So J is negative 60. And I do momentum final minus momentum initial. Okay, the initial momentum, it had a velocity of, what was it? 10. So here's how you calculate the initial. So this was 20. So I get negative 60 equals momentum final minus 20. So I add 20 to both sides. No, because I'm still gonna get the same thing. Yeah, sorry, this is wrong. I was right. You know what happened? They forgot the negative here. So you're not going to get 80, right? Because your initial was that, so plus, so that's going to be negative 40 equals momentum final. So if that's my final momentum, is negative 40. My mass is 2, my velocity is v, so I get v equals negative 20 meters per second. Yeah, wrong. You're wrong. Look at that. Wrong. I knew I did it right. And I think it was just because I messed up the sign on my thing here. All right. Practice some impulse, a practice problem here. It says calculate the impulse delivered onto a baseball that has a mass of 0.5 kilograms and is pitched and then hit by a bat. The baseball is pitched with a velocity of 25 meters per second and leaves the bat with a velocity of 35 meters per second. All right? So let's look at this. Let's draw a picture. You need a basic picture here. The ball comes in, it gets hit by the bat, the ball goes out. So one way is positive, one way is negative. It has a mass of 0.5. It has a velocity initial of 25. It has a velocity final of negative 35. Okay, these are important here. This is how you mess this up. So it wants to know impulse, right? So I know impulse equals F delta T. It also equals M delta V. So if I look here, I have velocities, right? So I can say impulse equals mass VF minus VI. J equals mass is 0.5. VF is negative 35 minus 25. And if I do that, I don't know my calculator. Let's see. Let me pull it up real quick. Calculator. I got 35 negative minus 25 gives me 60 times 0.5 gives me negative 30. So I'm going to get a negative 30. Should be my answer here. So let's see what we get. 30. Yep, negative 30. Perfect. All right. So now we're going to talk about different types of collisions, right? We're going to talk about, there's 3 different types, okay? So the first type we're going to talk about is elastic, okay? An elastic collision is on this side, okay? And the key here is that the total kinetic energy is conserved, all right, during the collision, okay? Not only is momentum conserved, so momentum is conserved, but also kinetic energy is conserved, okay? They're going to break apart and hit off and go other ways, all right? So if you add the initial kinetic energy, and total them up, that number will equal if you did it to the final, okay? That's what total kinetic energy means. It's conserved, okay? The next one we have is inelastic. Inelastic is more of a realistic collision where, okay, momentum is conserved, but kinetic energy is not conserved. It's not conserved. And what happens is you lose some of that kinetic energy into thermal energy, all right? Stuff like that. So, this is more realistic. If you ever seen like cars after a car crash, the bodies are all like crumpled up, right? The bodies of the cars crumple up. Well, that's designed to do that, right? If you watch like NASCAR or like Top Fuel dragsters, when they wreck, it looks like the car explodes, right? Well, they're designed to do that because what happens is it takes some of the energy away from the driver, right? So all the energy doesn't go into the driver. It goes into breaking the car apart, thus minimizing the amount of energy that goes into the driver, right? In the olden days when the cars were like steel and they wouldn't break apart or crumple, right? Drivers would die from, crashes that were like, didn't seem that bad. It was just, there was so much force going into them because all the force and energy was into them instead of, used to dissipate around them. Okay, so inelastic, the key here is to remember that momentum is conserved and kinetic energy is not conserved. All right. And then the last type we have are perfectly inelastic. All right. It is the same as inelastic, except the objects are going to stick together afterwards. All right. They're going to stick together afterwards and move as one. Okay, but remember, momentum is conserved. Kinetic energy is not. Okay, so remember, elastic, both are conserved. Inelastic, momentum's conserved, kinetic energy is not. Perfectly inelastic, momentum's conserved, kinetic energy is not conserved, and they stick together afterwards. Okay, there's a definition of three. Okay, let's go ahead and look at this. Oh, no, momentum conserved for both. Okay, good. All right, so we have two blocks, mass 2m and m, head towards each other, sliding over a frictionless surface with speeds 4v and 6v, respectively. After the collision, the M2 mass is at rest and the M mass has a velocity of 2v to the right. Was the collision elastic or inelastic? Okay, so let's look at this, okay? So regardless, momentum should be conserved. So that I'm going to look basically, to determine if it's elastic or inelastic, you have to look at kinetic energy, right, to see if that's conserved. So if you look at this, the total kinetic energy here should be decreased, right? Because if I look, my velocity here is 0, right? So that's 0 kinetic energy. And I have 1/2 m2v squared. Well, right away, I can tell you that this has more kinetic energy than that does right away, because it has 1/2 m, the same m, 6v squared. It has a lot more kinetic energy than that one does, and this one still has kinetic energy. So it's lost kinetic energy. So therefore, inelastic, since kinetic, so this should be A. Let's see, did I get that one right? Yeah. All right, since kinetic energy was not conserved. All right, collisions in 2D. It's the same as collisions in 1D. It's the same as collisions in 1D, except you have to, take the velocity in each direction. So let's look at the example here. So looking at this, I have the orange ball and the green ball, right? This ball is at rest, so I know the initial momentum is 0. This ball is only moving in the x direction, so I know it has only momentum in the x, right? So to look at this, I know in the y direction, my momentum has to equal 0. But it should make sense that, this one's obviously going to be traveling upward because it's going to hit and ricochet, and this one's going to be traveling downward. So what this means is this momentum here and this momentum here have to equal P1 in the Y has to equal P2 in the Y, momentum above, or row of 2, right? Because it's 0. It has to equal 0 in the Y direction because neither of these are moving up and down initially. So if this one's moving positive, this one's positive, and this one's going to be negative because it's moving down, all right, they have to equal out, so therefore they equal 0, right? That because the total momentum in the Y direction have to equal 0. Now I look at this, the total momentum at before is going to equal P1 in the X. That has to equal P1 in the X final plus P2 in the X final. So both of these are going to be moving in the X direction also, but if you add these two up, it's going to equal the total momentum before, okay? So it's just saying that momentum is going to be conserved now in 2 dimensions also. All right, so let's look at this. A metal sphere of mass m is traveling horizontally with a speed of 5 meters per second. So again, the one sphere is at rest and the other spheres only move in the X direction, right? After the collision, the original sphere has a velocity components of velocity in the X is 4, velocity in the Y is 3. What are the velocity components of the other sphere after the collision? So I know in the Y direction, right? I know in the Y direction here, my momentum has to equal 0. So if I look here, this is 3. To get the Y to equal 0, the other Y has to be negative 3. So if I look in the Y direction, the heck, they're both X's. Sweet. Well, the only one that has a negative 3 is this one, right? So let's look. Would one make sense here? Yeah, it would make sense, right? Because I'm going to add up my velocities. They both have the same mass. They have the same mass, right? So if I get the velocity add up, that's 4. We would need one more velocity to get the same kinetic energy. So yeah, this is going to be D, even though it says X twice. Sweet question. Sorry. See if I got it right. D? Is it D? Yep, D. Good. All right. So how you go about solving these problems? Pretty easy. Choose your system. Make sure it's closed, isolated. You're going to draw a diagram of the before, okay? Then separate it by the collision or explosion, whatever happens. Then you're going to draw the final situation. So you're going to have a before and after picture, just like I had. And then you're going to ask yourself, hey, well, one, make sure you label the directions. I think, yeah, coordinate plane system was next. So make sure you label which way is positive, which way is negative. And you have to keep it the same for before and after. So for the before picture, if you have right positive, you have to have right positive in the after picture, okay? Next, so that's what I just said. Apply this equation right here. Right? Initial is equal to final. And then you account for each, okay, you account for each object. So if there's 2 objects moving, you have 2 MVs. If they combine, add the masses, stuff like that. So yeah, if it's also elastic, you can combine the kinetic energy. That will be equal, and then you can solve for unknowns. All right, that was your lecture for momentum impulse. You can now start working on your momentum practice problems. There is another video for that to walk you through those. But hopefully that was a good introduction here.